Good afternoon, everyone. I'm here today to talk about a new tool that I wrote in open source. It's a Python tool, and it's available actually right now. It's called Ghidriff, and it's a Ghidra binary diffing engine. Now, if those words don't make sense to you, I hope to explain them during our talk. But I'll start with a little bit about who I am. You can find me on social media at ClearBlueJar. I'm a security researcher at ClearSec Labs, and I'm an open source dev. I've got several kind of InfoSec tools out there on GitHub you can check out. I love writing about my research. I do that on my blog. And about 3 years ago, I wrote something called CVE North Stars. And really what that is a tutorial on how to do patch diffing of recent CVEs. I found that to be a great way to get started in vulnerability research, is to start with a known vulnerability and then go try to reverse engineer to see what has happened. And so I'll talk a little bit more about that in the talk. That's kind of who I am. We'll start with the name. I think the name works. Ghidra and binary diffing together is Ghidriff. I have another cool tool called GhidraComp, which is just a command line decompiler, and I think it'll stick. But my main motive for this whole talk is to get you to try this command, pip install Ghidriff, and then run it on the command line with two binaries that you want to compare. If you're allergic to Python and maybe allergic to Java, which Ghidra runs with, I do have a Docker container for you, so you have no excuse really after this to try it out. And so as I say all these words, you might have some questions like, what is binary diffing? Maybe you're familiar, but maybe you're not. Ghidra, if you're not familiar with that, it's been around about 3 years, and I found it a really powerful framework for reversing binaries. Python, why we're using Python when Ghidra is written in Java, I try to explain that. And then this last line here is YADT, yet another diffing tool. I'll try to explain why I wrote another one. So here's our schedule. We'll get on the same page for binary diffing. We'll understand that together, what that is, how that's useful. We'll talk about background motivation. We'll dive into the internals of the tool, and then we'll walk through some CVE diffing examples, which is a great use case for binary diffing. So let's begin. Binary diffing. What is that? How is that useful? If you think about it at a high level, really binary diffing is comparing two binaries across time, a new version and an old version. You want to understand what has changed about it. There might be some functions that have been added, some functions that have been deleted, and functions that have been modified. The whole point really is kind of to filter out the noise, everything that stayed the same, and just look at the differences. In academia, binary diffing is called binary code similarity. This paper out here compares about 40 different tools that kind of do binary comparison. There's only 3 ones that I really know about or we'll talk about today. But we might know it as bin diffing or patch diffing. Actually, right now, if you Google patch diffing, my tutorial has a pretty good SEO or something because I've got the #1 hit. I'm not sure how long it's going to stay. But patch diffing is just a form of binary diffing that's looking at a recently patched binary, a vulnerability comes out, a CVE is assigned, the binary is patched. You look at that one and the one before, and you try to see what the difference is, and that's what kind of patch diffing is. So reasons as to why we might do this. There's 3 primary reasons for binary diffing. Reverse engineering, say you're 80% through reverse engineering your binary, maybe 85, and you're about done, and then this new version of your binary comes out, you're like, no, I do not want to do that again. You can leverage binary diffing to kind of match up those functions and port your previous reverse engineering work to the new binary. So that's one good use case for diffing. For vulnerability research, and that's probably what I use this for, kind of what my tool is geared towards, is you can go and see for yourself kind of the changes that happened underneath for a recently patched vulnerability to see if maybe what the root cause was, or maybe if they didn't fix it well. So it's useful for that. For malware analysis, you might use binary diffing to track 2 different versions of malware over time and say, oh, this binary or this malware is using this function which matches this function from this previous. So maybe a lineage for malware, you could use it to compare the 2. This is a tweet from Howard Flake. He's one of the original authors of BinDiff, and he says this: it's almost as if variance analysis and patch diffing is useful. And what he is quoting here is Google Project Zero's report stating that half of the O-days that came out in 2022 were actually just variants of previously known bugs. So attackers are doing this. This is a good way to jump into research. This is one of the use cases for patch diffing. So how do we do it? You could go and ask Bing, how can I perform a patch diff? And Bing says, I got you. Here's what you do. You take the original source file, and you take the new source file, and you run diff on them. And that works well when we have text and when we have the source, but what I'm talking is about when we don't. What I'm saying is when we have a binary and we have this big hex dump, and if you try to compare two binaries and their hex bytes, it's not going to look very nice. You're not going to be able to understand what's going on. But we live in the day and age of modern software reverse engineering frameworks. We have Ghidra or IDA. And what they can do is they can take this hex dump here and they can turn it into something we can understand, maybe an assembly listing, or actually the pseudocode or decompiled version of that. And they can help us understand all these complex relationships in a binary, the call graphs and how these functions are connected, and allow us to build our tools on top of that. So in effect, SRE tools, they distill these binaries into objects and in relationships that we can compare. And that's how we can actually do the diffing that we're interested in. So let's take a look at the diffing tools that are there. Remember, their purpose is to find all of the added, all of the deleted, and all the modified functions and data between two binaries. And is that hard? It sometimes can be hard. That's what these tools are here to kind of solve. Back in 2004, Halvar wrote this paper, Structural Comparison of Executable Objects. It was a paper about kind of the what BinDiff was doing and how it was using the structural graph to compare two functions, how that was unique at the time, and so revolutionary at the time, actually. But he talks about the problem of asymmetry, of reverse engineering binaries. He's basically saying a small source code change can really affect what the resulting binary looks like. And what he means by that is, the registers might be different the next time the binary is compiled with a small source change, or the compiler might optimize a different way and different paths to be taken. So this makes it difficult to kind of understand which changes were actually because of source code change or functionality change versus what the compiler has done. So every diffing tool is trying to solve that problem, to bring this symmetry back to this asymmetric problem of reverse engineering binaries. And let's take a look at kind of what the main contenders are today. The most popular one is BinDiff. It's been around for a while. There's a slide here actually from 2004. So here we are almost 20 years later, still talking about patch diffing. This is Halvar Flake's slide from Black Hat 2004 talking about BinDiff. And he says this, 2004, he started a company. They created a product called BinDiff. It really became the verb, that when we talk about patch diffing, we're like, oh, you BinDiffed it. And so here's what his tool, the tool looks like. And basically it's a big table that lists all the functions and it tells you how similar they are. You can click on a function and it will show you a side-by-side comparison of two functions, the control flow graph. You can kind of easily see the differences that way. You can zoom in and kind of see the basic block level of the assembly of what's changed. It can help you start to understand how this function has changed actually. And in 2019, Maddie Stone did a presentation called What's Up with WhatsApp. She reviewed, I think, 5 or 6 different patch diffing tools at the time. The winner for her was BinDiff. It actually found the matches she was looking for in her WhatsApp binary. I pretty much agree with all the bullet points she has here. I think the only downside to using BinDiff is you don't have a built-in pseudocode or decompiled view. But other than that, the matching is excellent. Another tool out there is called Diaphora. Now, I've not used this tool myself, but from its README, it's actually a plugin for IDA. It's been around since 2015 or so. It has that side-by-side view that we're talking about, that pseudocode diff view you can see in the bottom section here. And similarly, it has a table at the top where you can sort your functions to see how similar they are. In 2019, it didn't work for Maddie Stone. But this project is actively maintained, is really popular. Its recent release has a ton of new features, and I have friends that use this tool. My experience actually is with the version tracking tool. Now, this is a native tool built into Ghidra, and I have a lot of opinions about this. This is what I wrote that tutorial on, and I have a lot. This is kind of how I feel about the version tracking tool in Ghidra, and I call it the Millennium Falcon of patch diffing tools, and not because it's fast, but more because it's going to break down. You're going to kick it, but have to hit the side of and the engine is going to start back up. But it will get you there in the end. And so this is what it looks like. Can be hard to see from there. The slides are better on PDF, but the top is a function listing again. You can sort by how similar things are. When you open up this view here, it pops open two code browsers, both for the source binary and the destination binary. And basically those browsers would come up like this. And when Maddie Stone did the review back in 2019, she forgot Ghidra. But I'm here today to fill in that gap. And here's my review of Ghidra's built-in version tracking tool. It does have some insightful match algorithms. There are some well-known ones even introduced into BinDiff that are lacking in Ghidra, so they're not there. It doesn't have a pseudocode diff view side by side. It could, but it's not there today. Its similarity scoring is confusing. I talk about this in the tutorial. You have to understand what those things are to actually sort them properly. A bit slow, but again, it will get you there in the end. And so those are the three tools I'm going to review, and then I'll have to have you guys review my tool someday. But let's understand what maybe a typical workflow would be for patch shifting two binaries. Typically, you have to go and get those binaries. Maybe you download the new version and the old version. You have to import those binaries into your SRE framework, whether that be Ghidra or IDA or another. You have to run the analysis on the binaries, then run your diffing heuristics, and then do your analysis. In the case of BinDiff, you can export the analyzed binaries into BinDiff for further analysis, and there's quite a few steps there. If you're going to do this on Windows today, the way I would do this, I would wait for a patch Tuesday to come out, and MSRC will publish, their 60 or so CVEs. You can go sort by topic. In this case, I'm searching for kernel. There was 6 CVEs back in September. You can click on one of those CVEs, and from there you could pivot to the build number on the far right-hand side. The build number itself will tell you which binary to go and download, and then you download that one and the one before. Now, there's a patch diffing, I'll call it a patch diffing saint out there. He has built a website that auto-catalogs all the Windows OS files, puts them in this nice table, and gives you direct download links from Microsoft to go and get the binaries that you need. So if you're doing Windows, there's no better source for Windows OS files than the site called WinBindex. So basically, you could go download the right versions of the kernel. You could import them into your SRE framework. You would load them up and do your diffing heuristics, or alternatively, you could go and export those into for BinDiff, the bin export, and then analyze the diff once again in BinDiff and see what those differences are. And that's kind of the basic workflow. Download your 2 files, run the binaries through analysis, do the diffing. But kind of under the hood, like how do they work? As I mentioned before, every bin diffing tool is tied to some SRE framework. And my tool as well, it rides on top of Ghidra. All the analysis I can do is because Ghidra has analyzed the binary, has identified the functions, has identified the data, and I can take those 2 binaries and compare those across. All the tools really kind of do the same thing, where BinDiff can be used with IDA, Ghidra, or Binary Ninja. Diaphora is attached to IDA. Version tracking is the native tool in Ghidra, and my tool as well relies on Ghidra. All these tools are playing this game of function matching. They have to find all the functions, match them up across the board, and they typically start with function matching heuristics that are fast and accurate, and they progress towards more speculative ones as they go along. For some reason, they all have different names for it. BinDiff calls them matching algorithms. Diaphora calls them matching heuristics. Ghidra has gone with correlators. But they're all meaning the same thing, and they all generally are using these 3 matching methods, whether that be a syntax comparison, where they take 2 functions and they byte for byte compare them, and then take the hash and see if they're the same. There is a way to do semantic comparison, meaning the functions mean the same thing. In my research, most heuristics don't use semantics. I think that's a really hard problem. Maybe emulation would be a way to do that, but structure is the other way that BinDiff kind of brought in in 2004, a way to compare the call graphs and nodes of 2 functions to see if they're the same. A quick look at a syntax function. You're not going to be able to read this probably from where you are, But all this function is doing is going byte for byte, putting them into a buffer and hashing it, and that's how it's doing the correlation. That's an exact bytes hasher. For structural matching, you can look at the edges and nodes of two graphs here, or the control flow graph of two functions, compare those and see if they are the same or not. But every tool is really looking to provide you this complete match, because once you have that everything matched up or not, you can classify those functions within the binary. Everything that was not matched in the old binary, we classify as deleted. Everything not matched in the new binary, classified as added. And then everything that was matched but is now different is modified functions. And all of these things become interesting in your analysis. With that full view, you can start to see, which function was deleted, which function was added, and start to speculate why. Now, I'm using Windows examples here, but you can tie this to other types of binaries, but Windows examples make really good slides, because you can start to see kind of which functions were added. In this case, this was a patch shift of a CVE for a Windows binary. And they added some functions called isValidFilePath, safe delete file by handle, convert path to long UNC. These are all things that you would add to more safely delete a file on Windows. If you were to jump down to the function that was modified, that are using these new functions, you'll start to see like, they deleted this delete file call, and they replaced it with this safe delete file call. Well, that's a pretty straightforward example of patch shifting, seeing, what did they fix here? And so the point is, patch shifting is not like a magic bullet. It's not going to tell you which functions are relevant, but it will limit your view to the ones that could be across the version change. So that's kind of patch shifting, binary diffing. I hope we're on the same page, how that might be useful. Now let's talk about why did I write another tool. BinDiff is really good. These other tools are really good. And I'll try to explain. So this is a screenshot of my tutorial. And basically what I did with this tutorial was teach myself patch shifting, and then I just shared it out there. I walked through a series of Windows Print Spooler CVEs back from 2020. And every month a new CVE was coming out for the Windows Print Spooler. And what you could see by patch shifting these CVEs was that they weren't fixing the root cause. They were kind of putting a temporary fix on top, and people were finding new CVEs and workarounds. And what you could see with the patch shifting is that this is why. It's not a new topic or a new thing. This is Project Zero doing patch shifting to find kernel bugs back in 2017. This is about, again, the time frame I was researching patch shifting. If we fast forward, actually, this is an article from Charles's bug here, but someone patch diffed that CVE when it came out. And so basically what they had were the details. They reverse engineered what they fixed even before Charles's talk came out. Now, Charles's talk was very good. I have to admit that, and we had more details from that. But it's a way for you to go and look for yourself when things aren't clear. When the vendor releases an update, but it's not clear what they fixed, you can go and do this. I teach a training called Patch Diffing in the Dark, and this kind of stemmed out from my tutorial and my experience with patch diffing. But the basic idea is, from a CV description, you have a lot of context. You have like a scoped reverse engineering problem from this one sentence. From here, we see an example that says there's an integer overflow in this version of WhatsApp. Okay, we now know the version, give the one before. We know what we're looking for. It even gives you more context. It says it's an RCE in an established video call. And so that scopes it down even more and gives you a nice, concise, Friday night project for you guys to go do when the conference is over. I mean, I'm not sure what you guys are up to, but these are the conclusions that came from patch shifting. It's a way for you to go and see for yourself what the changes were. Not trusting like a POC or a blog post. You can go look and to see maybe what the root cause was of the vulnerability, or maybe see that it wasn't fixed completely. It definitely is a fun, scoped RE project, and it just, this is just what became a part of my kind of day-to-day in my research. So I started doing patch shifting quite a bit. I kind of was following this long workflow you see on the right-hand side, where I was, that list I had before, import the binaries, do the analysis, run the tooling, look at the analysis. And after doing that for so long, it gets a little bit repetitive. And so I want to look high level first and then dive in. So I'll ask, what do we do when we find a task that is repetitive and tedious? Typically, we write a script. And that's what I did. About a year ago, I started Ghidriff, and it was a single script called Simple Diff. .py. Even called it simple diff because it was very naive. It was using basically the function names. And again, we're looking at Windows. We had public symbols. It worked okay, but definitely had a lot of false positives. And so what I'm trying to say is Ghidriff, for me, was born out of this necessity to get around these pain points and really curiosity of how does patch diffing work. And so let's walk through some of those pain points. The workflow was one. That was a primary one. There was these 8 steps before, and for me that was too many. After you do that about 10 times and you get tired of clicking around, what I needed is kind of what I built here, this a command line tool that would kick off the diffing, do the full workflow, and come back and show me the results. And so now I think I have that full workflow down to 3 steps, which is a lot more feasible for me. Now in Ghidra, I don't have that side-by-side diff view. What I was doing was I was taking the code browser from both sides and copy-pasting that into VS Code and then looking at diffs. And that diff looks nice there, but again, manually copy-pasting those out is pretty painful. And then the sharing of the results. For most of the tools out there now, I think a lot of them have like an export to an image where you can share your results that way. I don't really know of another way they have for sharing results, but I wanted to really overcome that. I'm a big fan of Markdown. I use it for taking notes, for writing blogs, for writing my reports. It is used everywhere, I feel like, or everywhere, at least maybe that's relevant to me as a computer nerd. And then I even talk about this in one of my blogs. I basically want to mark down all the things. I wrote my slides actually in Markdown, which maybe you can say, yeah, we can tell, but it's pretty useful for kind of capturing everything as text and rendering. But anyway, I wrote a tool that would actually spit out a call graph from Ghidra, and it would draw a graph from text. There's a library out there called Mermaid.js, which is also available to you on GitHub or GitLab. Or integrated by default. And you can write a markdown that looks like this and translate that to like a Gantt chart or a flow chart or kind of several options for you. And so as you can guess, my output is markdown, and we'll talk about that here shortly. For curiosity, when you write your own tooling, you learn a lot. You understand what the complexity of it, why this is a hard problem, where there's some issues might be. I learned a lot about Ghidra, its program API, how I could leverage that to do the binary analysis. I was able to get around my pain points. So really just a slide to encourage you to go and try to write your own tooling. All right, so that's my motivation. Why did I write another tool? I had those pain points. Let's talk about a little bit of the internals of the tool. Well, at a high level, basically what it takes is 2 inputs, 2 binaries as an input, and then it spits out all the Ghidra project files. So it will create you a new Ghidra project, which you can go and analyze later. And also a markdown report. It captures all the diff results in a JSON file, and you have the option to export as HTML as well. Kind of my design goals is I wanted it to do patch diffing. I wanted it to have all the software engineering aspects of a good tool. And I want that sharing results, that the social diffing, like GitHub has social coding. I wanted social diffing. I wanted to be able to take my results, share those with a friend, post those somewhere, and make that easy to do. So what did I go with? Well, we knew about Ghidra. Ghidra, free, open source. The support is really good. When I have an issue or when I have issues with Ghidra, I submit an issue. They're pretty responsive. A lot of times they teach me things like, no, that's not how that works. And I'm like, oh, okay. And then, or actually the community, even outside the Ghidra team, seems to also chime in as well to kind of teach me things as I go along. So if you're looking for, I don't know, it seems to have a great support for the project. And the programming API is pretty good. It is Java, and we'll talk about this in a second. I'm using Python to access Java, and this is we'll talk about that here. I want it to be simple. This is the full Python package here. If you dive into the package itself, it's only about 8 or 9 source files. I feel like it's pretty straightforward to understand. And the basic flow is we're parsing the arguments, we're setting up a Ghidra project, we're analyzing those binaries, we're doing the actual diffing, and then we're generating that markdown. And those are kind of the 5 steps of the tool, kind of that big high level. One question is, how do we actually call Java code from Python? I did a blog post about this because I didn't know the answer. And I kind of researched several different tools that allow you to use Python to access Ghidra. Ghidra itself has built in something called Jython. And Python itself is an implementation of Python in Java, but you can only use up to Python 2.7, and I wanted to use the latest. There was another project out there that ran an RPC server in Java, and then from Python you would call RPC and communicate across, but it was incredibly slow. I'm analyzing thousands of functions, and this thing, that did not work for me, but what I found was this tool called Ghidra. Now, Ghidra it says here, is a Python library that provides direct access to the Ghidra API within a CPython interpreter. And it relies on another package called jpipe. What it allows you to do is in Python, write code that looks like this. It says, with Ghidra.open program, analyze some binary, and then that auto-analyzes the binary, and then you have direct access to that object within Python. And you can step through this. You can inspect the Java classes in objects from VS Code, even though you were in Python. And it's really powerful. It's actually pretty fast because it's enabled by another package called jpipe. And what jpipe does actually is from CPython speaks directly to the JNI of Java. There's not really any overhead there. There's a shared memory space. And so when I'm doing my analysis, all 8 of my cores are kicked off and fully engaged. And so I found it to be actually pretty fast doing the diffing. The way I made it extendable is I kind of built a base class called Ghidra Diff Engine. And that engine kind of does 3 steps for you. It creates that project, imports the binary, and analyzes the binary. And once it's done that, you have to implement for yourself a function called find matches. And the find matches function gives you programmatic access to both of the binaries. And then, there's some magic in there as the code goes here. And I've implemented 3 different versions of this so far. And my latest one has kind of all my knowledge actually squeezed into that last one there. But I had evolution over time. I learned about simple diff, kind of doing naive matching. I learned about bin diff structural matching. I added that in there. And then, for example, the simple diff function matching was just looking at the simple names. If your simple names matched across 2 binaries, you're the same. If your name and your function length were the same, well, you're the same. And there's definitely some false positives with the simple matching. This is the code for that, but you can't really read that from there. But slides might be there or be more helpful. Again, the structural graph diff implementation did all those things and added some structural heuristics in there. And we'll be able to see this too much. But the last version here has about, 12 different correlators that I'm using currently. And I've used this very well against Windows and Android binaries. And you have to go see the code, what they are. But there's 12 in there right now. Some are directly from Ghidra. Some ideas are from BinDiff. And some are just more speculative, like using strings and things like that. So each of those function matching heuristics are called correlators. Here's an example of one. Essentially, what you have to implement is a hashing function. Doesn't have to do any hashing, but you're going to run this function and you're going to run this hash and all the functions to see if they match across 2 binaries. And that's not even that important. But look at the code; you can kind of see the details there. I wanted it to work well, so I do have it built into GitHub Actions. Maybe I can protect it with the tool I just heard about. But I have some automated testing built in there. I'm testing across versions of Python and Ghidra to make sure it works pretty well. And they're Dockerized so that, again, you can try this out without actually installing anything. For sharing results, all of the diffing results are captured in a JSON file, and they'll capture like which functions were added and deleted and modified, they're classified, and then some more details about the diff that I just ran. For social diffing, basically the resulting output, and this is maybe the first look at that, is a summarized output that you can copy paste into a GitHub gist or a GitLab snippet. You could put this into your blog if you wanted to, or your GitHub README. It's kind of because it's Markdown, it's enabled for all these other systems, and it looks pretty well. These are all deep links. You can click on the link for the function. It jumps right down to the function you want to look at. And it kind of gives you that high-level view of what were the changes were. They don't always look so, in this case, there was only one modified function. They're not always so concise, but here's some good examples anyway. All right, so now we're on to features, and I've kind of already demoed some of those. But the command line, I think this is the biggest feature for this tool, is that the whole workflow is now on the command line. You don't have to start up any software reverse engineering frameworks. I mean, they are started up, but they're started up for you. And basically, you can run just a command that looks like this. Now, there are more options than just that, and you can't see that as well, but the most essential ones are the two binaries, the two inputs. You have some options for changing where to store the Ghidra project files. If you have symbols that you want to apply to your Ghidra analysis, you can define that here. For debugging, you can turn off threading, which makes it a lot slower, but it's useful for debugging. And there's several options that you can run through here. For the JVM, so when you start your Python project, or when you execute Python, it's going to kick off a JVM to run Ghidra in. And if you're analyzing 8 Windows kernels at the same time, you're going to want to bump up that RAM so this thing runs a little bit faster. And so there's some options for that as well, and just a few more. So if we take a look at the summary table of contents that it produced, you can see here this is a diff of the kernel. And you can kind of see, we'll jump through all these. That table of contents gives you that high-level picture. A quick look at what's changed. It does dynamically build you some graphs. For example, this is Mermaid.js, and it's not the best-looking graph, but it is accurate. You can actually copy-paste this into your blog post. You can copy-paste that into your report that you're submitting. And this is a quick view of what this looks like. There are some more graphs in there to say like, oh, here are the matches that were used to actually do the matching, and some more things like that in there. I've added another feature called metadata diff, and this is metadata about the binary itself. This is showing you some things like, the compiler across the two binaries was the same, but the number of instructions have changed, and the symbol number has changed, and maybe the PDB has changed for, in this case, this Windows file. So a quick view of some things that are not to do with the functions of data, but to do with like the options used by the compiler. Strings is useful generally when you're doing diffing. So this is a string diff of all the strings within two binaries. It provides for you this a way to repeat the diff that you just did. So this is the command line that was used to generate this diff, and that's included in your report if you wanted to repeat the work. If it's a Windows binary, it can actually rebuild you the original download links from the binary itself, because Microsoft hosts not all, but hundreds of their files, and there's a algorithm to generate the actual download link. And so I include that for Windows files. And finally, if we go and look at one of the functions that was modified, at each function you're going to have some information like how similar was it, what was the ratio, how was it matched. In this case, it was the symbols hash match. From there, you can compare side by side some more metadata about the function itself. And in this case, the length was changed, the call, like who calls this function changed, and that's it for this case. I provide a call diff. So this is like a high-level view of which functions called yours, and that could be useful for quick analysis, and we'll see that here in a few demonstrations. And eventually, you get down to this unified pseudocode diff that you can't see. But if you zoom in, you can start to make sense of, oh, these are the changes that were made. And sometimes this unified diff gets a little bit hard to see. It's a little bit cloudy. I can't really see very well, and the side-by-side is a lot cleaner. But we have an issue actually with Markdown, and that it doesn't support HTML styling. Typically on GitHub or GitLab, it's going to not show you the style. So in VS Code, you could look at the side-by-side diff and you'd have the colors. But if you do the same thing on GitHub, the style would not be rendered. It kind of just shows you the text for what it should be. And so the side-by-side diff doesn't look very well. So I did just build a kind of simple site. I forked one of those HTML previewer sites you guys may have seen on GitHub. And I called this, diff, just HTML preview. And basically what you can do is copy paste the results from my tool into a GitHub gist, and then plug that same unique identifier into my previewer, and it will go and parse out that markdown file and bring you all the diffs so you can see them side by side. So you can click on these links. That same unified diff we saw before now becomes much cleaner to see. And if you zoom in, you're just like, oh, this is what has changed, an easier way to see it. So this is more of a workaround, because there actually is one limitation for Markdown, and that's it. There's probably more. Okay, we're doing well. Okay, Ghidriff in action. What do we actually do? How do we use this tool? Where is it useful? If you wanted to go and see all the changes for the Windows kernel, the most recent one, or if you want to go back in time, use that winbindex site, download these two files, and I will quickly walk you through the output that you again can't. This is what it would look like. It would print off for you all of the parameters that you use to run this diff. It would go out and download the symbols from the Microsoft server. itself, if it can find them, and then apply that to the analysis. It would do the analysis, it would run all the diffing heuristics, and finally it would output you, a markdown file and a JSON file for you to go and paste into GitHub. And then from there, it's much easier to see the results. You can click on those links and kind of go from there. So that was this is a full Windows kernel diff, and the kernel has about 32,000 functions across 2 binaries. And what you see here is about 11 different functions that have been changed. And so that's, again, a quick way to see the changes across time. If you're looking at CVEs, and this is primarily what I'm using this for, we'll demonstrate here kind of how this can be useful. So back earlier this year, there was a CVE called 21768, and there's a great blog post on it. This is by Valentina and Ruben from IBM. And there is Patch Tuesday, Exploit Wednesday. And that's the idea that, every Patch Tuesday, the CVEs are patched for Windows, and by Wednesday, you can reverse engineer those and be exploiting them. And this was an example blog of them actually doing that. And they used Ghidra and bindiff to find the differences between the 2 binaries. And what they discovered was that there was a missing user mode buffer check called AFD notify remove IO completion. So if you wanted to repeat that same research those researchers have done, you could use Ghidriff. You could download the vulnerable in the patch version. You could run Ghidriff on those binaries, and what you would end up with is something that looks like this. And just what you notice here is, that same function they identified as the one being modified shows up in our results. And if you were to go to look for that diff, there was a 1-line change added here that was protecting this user mode buffer so that it would blue screen if it wasn't the right case. So this is just an example of us using Ghidriff to do what other researchers have done. I've got one more of these. CVE 2023-21769. This was an issue with Windows message queuing service called, they called it QJumper. From this blog post, you couldn't tell which binary actually had the issue in, but you knew the service. But on GitHub, someone had posted a POC and the call stack from there. And from the call stack, you can identify this MQQM binary and the actual function that had the issue. And so what I'm trying to say is from the GitHub POC and the blog post, we knew this. We knew that the packet parsing code in this function in this DLL has an issue. So again, if we want to repeat that with Ghidriff, you would download that vulnerable and patch version. You could run Ghidriff on the command line. And what I'm showing you again is that we can identify that same modified function. Now this time you might want to look at the call diff and to see which functions were added to this. And they added several things called get next section safe. And these things that probably are handling some kind of parsing issue in there. If you look at the side-by-side view, we can go from there. And then not only can you repeat others' work, but you can also go and look for yourself. You can go root cause your own CVEs. Taking a look at this one, this was published back in, I think it was actually September. It was called Windows System Assessment Tool. I didn't really know anything about this CVE. There was no blog post or POCs, but from that description, you can say, oh, on my host Windows system, I have this file called Windows System Assessment Tool. Well, it's also you need admin to run it. So that kind of lines up with what we just saw with the CV description. Elevation of privilege, Windows System Assessment Tool. So repeat the same thing. Again, download the right versions, take a look at the diff, and what you see here is, one function was modified. They added something called delete file via disposition. If you look at the call diff, again, we see, an unsafe API being removed and a safer API being replaced. Windows delete file is subject to a time of check, time of use vulnerability. And so by the time you actually go and delete the file, the path may have changed. If we look at the strings diff, that kind of points that way. It says this is found to be a symlink. So likely what they've done is remove the unsafe API, replaced it with a new one. So we're speculating just from doing the patch diff at the high level, using Ghidriff and nothing else, this was an arbitrary delete. And so that's kind of the power of patch diffing. You can go and see for yourself what has happened, what has changed. I'm running low on time, but here we go. So I posted this earlier this month, and it was my introduction to Ghidriff. I think I had a good response. I actually had the current maintainer of bindiff from Christian from Google actually comment saying, "Oh, I probably should update some of the Ghidra things." And then in jest, I responded with this. But it's just fun to kind of have that back and forth. But I'll say this: Ghidriff, it's not perfect, but I found it to be pretty good. There are some known issues. I'm going to skip to the unique benefits. It's simple. The entire stack is open source, and it is command line. So I think that's unique about it, and then powerful for automation, for your analysis, for doing quick analysis. I think it's social because of the markdown. Really, that's the reason. I've got some things coming soon. I want to add call graphs to the output, so you can analyze. This modified function is here, but how do I get to that? How do I approach that function? And in the end, patch shifting, I'm going to say, it can provide the insight that you need to understand modern vulnerabilities. Ghidriff can help you get there, or patch shifting in general can. I'll encourage you to try it. And I'm just going a little bit faster because I wanted to have a little bit of time for questions. I'm not sure we are. It's going to be on that. But try it. Yeah, it's definitely a fun evening project. The CV scopes you down to a version of the binary, something to go look at. And it scopes it down so you're not looking at the whole aspect of the software. You're focusing on that vulnerable code and kind of frames that for you. So we covered quite a bit, but I will open it up for questions if I have time. Okay?
Any question in the room?
Thank you. First of all, a very cool talk, very insightful. And I have two questions actually. The first one is about the distance between versions where it is applicable. So in your experience, maybe how many versions should be between the two you compare, so that it's still useful and not everything is just displayed and modified or deleted? The second one is more towards the applicability, maybe for scenarios like malware research and malware diffing. Since with malware, in my experience, a lot of the time you have obfuscation, which obviously will be a deal breaker here.
Sure.
So it would be quite nice to introduce maybe pre-processing steps that the user can do or can also be conducted automatically before the Ghidriff workflow starts. So I wanted to ask, how easy would it be to include these pre-processing steps? Or would I just have to basically
I'll try to answer both of those. The first one was, how close do these version numbers need to be for it to be accurate or useful? I've done this before where there's thousands of functions that I cannot match because that distance is too far apart. I don't have the one right before. I've got 1.5 before. And that will vary by platform. That will vary by kind of which application you're looking at, how much things have changed. For Windows, they're pretty precise on release dates, and you can kind of get those binaries. For others, like for Android, I'm looking at, APK download sites and seeing if I can find the right comparison. I can't always get that one for one. And so I'm going to say that answer will vary. So that's not a great answer, but that will vary with what you're using it for. But ideally, get that as close as possible, and that's where you are. But if you want to apply this to malware, or if you wanted to use this with Ghidriff right now, for maybe you've already reverse engineered malware, so you have analysis already complete. Is that kind of your question for the second part? Like, could you apply your already analyzed binaries to the diff?
Essentially, yes. So you would introduce pre-processing steps, which would actually remove at least a part of the obfuscation layer so that the binary comparison actually would make sense.
Right. So Ghidriff right now, if you don't have a Ghidra project, we'll create a new one and import those binaries in. There is actually an open issue with that very same question that came out the first week. Can I use an already analyzed binary to do my diffing from? That is a feature request. You can reuse the one that Ghidriff created, but I don't have the ability just yet. But it would be very simple. Simply point your Ghidra project to a new one, or to the one you've already generated, and then do your analysis on that already analyzed binary that you've done your pre-processing steps on. So today, you can't do that exactly. You can reuse a single project, but not multiple projects, if that makes sense.
Okay, thank you.
Yeah, we can talk more after.
And maybe we have time for one last question. There's one here. Can you bring the mic?
This one.
Here in the guy with the blue sweat. Thank you.
Thank you for the talk. Have you tried diffing binaries written in different languages? For example, Go or Rust add a lot of boilerplate and other function calls to the binaries? Does it make the diffing more difficult?
So I've looked across architectures, so whether that be 64-bit or ARM or Intel, but I've not done Go. And really, actually, this picture kind of describes it. I'm only going to be as good at diffing as my software reverse engineering framework is at pulling out those functions, reversing those functions. But the power of the tool comes from Ghidra, and then my tool kind of does the matching after the fact. So I can only be as good as the analysis is. And so I'm not sure actually how Ghidra's doing with Go right now. I think there's a couple plugins for it. Not good. Okay. So I'm not sure how much Go, but fix the analysis for the Go problem for Ghidra, then it would work. Or if other platform or other frameworks do it better, you can try diffing there. But my tool is applying to Ghidra. Yeah.
Okay. So if I have the Go plugin installed in my Ghidra installation, does it take it into account?
It would, currently it uses default Ghidra. So just taking, but you can install plugins to your instance. So I'm not using the GUI, but if the plugin is installed, it would actually apply to the analysis. And so it depends on your basic install on your machine. I don't know the answer, but maybe that's a good investigation to do. But it should actually just apply because I'm just using Ghidra.
Okay, thank you.
Okay, thanks again. Nice talk.
Thank you.
Thanks again.